Okay, the last one. Let's look at these real quick. First one. I see a pretty strong peak here at about 3,300. You can look at the exact numbers here. What does that say, 31? No, it says 3328. Is that right? It looks like that's 3328. That looks like OH, NH region, or maybe, what else could it be? SPCH. Do we even have any alkynes up there? Yeah, we do, right here. What else do I see? Magic line of 3,000. It's a magical line. Yeah? It looks like we have sp3CH. It looks like sp2CH, is that right?
Right.
And is that a carbonyl?
Yeah.
What is that, 15, 16? Is that 16 something? 1645? Comes down to 77. No, wrong one.
1639.
Comes down to about 4. 1639? 1639, is that what that is? That could be a carbonyl, it's pretty darn low. If that's an SPCH, the carbonyl is an ester. Ester would not be that low. Ester would be like 1739. If this is a carbonyl, it looks like an amide, right? Low carbonyl. Maybe an amide and an NH. Do we have? Also looks like an aromatic signature here, busy in here. It looks like aromatic amide with it, just one NH. Here?
No.
What's wrong with that? It's got sp2CH on the benzene ring. It's got sp3CH on the methyl. Got an NH. That could be NH. Low carbonyl for the amide. I mean, this one here is very darn similar, but that doesn't have any sp2CH. We got something to the left of 3,000. We also, it looks like aromatic here, right? Yeah? I think it's this one here. We can keep looking, but I'm pretty confident it's there. I just draw an arrow there. I saw a couple of you redrawing the structure. That's going to take you time to redraw structure. Just draw an arrow or put an A here and an A here or something. Don't waste time redrawing structure on the test. Yeah? How we do? What'd you put, Arfon?
I haven't watched the video.
Next one, I see a pretty broad, looks like an OH. Classical. Now, up on the newer instruments we have upstairs, modern day instruments, OHs aren't quite as broad. I don't know if I said that in the video or not. So be careful when you use the IR here, it's not going to be quite as broad, but that looks like an OH to me. It looks like we got peaks here. sp3CH, sp2CH maybe. There's no carbonyl. That's too weak to be a carbonyl. Carbonyl is going to be one of your more intense peaks. I don't know what that is. What is the position of that? 15, it's about 16 something. It's almost alkene region, carbon double bond. Instead of C double bond O, C double bond C, which tends to be weaker. What is the value on that peak there? 16.
1648.
What's the one about it, 1645?
Yeah.
Pretty close. It's either 1648 or 1645. It could be C double bond C. Instead of C double bond O. Mainly because it's weaker. Well, that kind of makes sense because if you have sp2CH, you need an sp2 carbon, and an alkene would give you sp2 carbon, right? Do we have an alcohol that has like an alkene in it
Yes.
as a choice?
Yes. Yeah.
Right there. Again, that's too weak. Where'd you go? One below. It's too weak to be a carbonyl. Yeah? Carbonyl tends to be a stronger peak. That's an alkyne. That's going to be a triple bond, carbon-carbon triple bond, about 2200. I don't see that. Well, let's look at the right spectrum. It also really doesn't look aromatic. 1600. I don't know what this is here. That's kind of odd. Is there any other possible choice, though? I don't think so. The second one is that alcohol right there with the alkene in it. Yeah, how we doing?
Good.
One on the side over here. Non-fingerprint values above, giving you peaks here. 3265, 2988. So that tells you that this peak here, it's labeling these peaks. What do you see here? There's no sp2CH. A couple strong peaks here. This one is apparently 2124. And 1718, that looks like a nice carbonyl. What is this here? 2124. Probably C triple bond C, because C triple bond N tends to be a little above 2200. Do we have a alkyne with a carbonyl?
Yes.
By the way, what would this be? Let's peek over here. If you got an alkyne, the terminal CH would be an SPCH. That could be that right there. SPCH tends to be about 3300, tends to be pretty strong.
Yeah.
That peak can often be forgotten about, but if you have an alkyne, one of the carbons has an H on it. Now, hopefully there is a terminal alkyne up there with a carbonyl. Because if it ain't, we're going to have to re-evaluate our peak assignments here. All right. Let's look behind door number 3. There they go. Do we have an alkyne with a carbonyl? Right here? That's an ester carbonyl. That'd be about 1730, 40 or so. What is the carbonyl? 1718. That's a little low for an ester. It may be because of this sp carbon actually acting as a withdrawing group. There's an H on the end, right? And CH is at peak about 3300, 3265. I think it's that one there. We had a carbonyl and then a paternal alkyne. That alkyne has no carbonyl. This triple bond, could that be this one? Maybe that's the NH. Maybe that's the cyano group. And then we can just ignore that big peak, right? That peak doesn't mean anything. Wrong. That's a huge peak in the carbonyl region. Looks like a carbonyl, yep. So you would not choose this because that has no carbonyl. So I'm thinking all roads lead to this one here.
So
Yeah?
that one won't be possible as,
I mean,
is that at the 3200, it's not possible to be an alcohol?
alcohol,
Yeah.
it's a little, it doesn't look like an alcohol peak. Possible. So what do you think it is? If it's an alcohol,
The one
what-
on the top, the OH with triple bond?
here?
Yeah,
But this is clearly a strong carbonyl.
there's a carbon.
There's no carbonyl there.
Alright.
So I'm thinking it's not an OH, because if it was, there's no choice. So it must be the SPCH. But you should look back in the IR handout. Look at it, terminal alkyne. That is one that has an H on it. You'll have both the carbon-carbon triple bond peak, but also the SPCH peak. So there's this SPCH there as well. Okay, that was a little, what hopefully you did a little practice, non-graded quiz in preparation for test tomorrow. I'll post the hard copy upstairs, but there'll be no video today. We did it in class. Okay, test format. Similar to quizzes, short answers. There will be some multiple choice. We'll also have IR page, which will be very similar to what we just did and likely your workbook. There could also be some IR theory questions in the short answer or multiple choice. Topics, you know all the topics. We have nomenclature, which was done by video, alkanes. My test usually begins with nomenclature question. And then usually on the first page, usually some multiple choice questions. You have plenty of multiple choice in the workbook for that type of format practice. What do we have? Topics. We have structure bonding, DUS, functional groups, hybridization, yeah, all that good stuff, structure. Physical properties, including solubility, melting point, boiling point, polarity, molecular dipole moments, all that good stuff. Acid-base chemistry, all the various things there. And we have alkanes, conformations, a few miscellaneous things in that handout. Conformations being the Newmans for rotatable alkanes and chair conformations for the cyclohexanes. Yeah? Let's finish up. Finish up the handout. One of them is purple, the other one is maybe gold. Yellow was the DQ page. I think it's gold. I think the first page we have completely done. Anybody have a name for this one on the right?
No.
I see a carbon with a chlorine. Two ethyls. If I'm standing over here, I see a chlorine straight up. Is there a chlorine drawn straight up? I see an ethyl to my right. Is this drawn with an ethyl to the right? Front carbon? Front carbon, I also see an ethyl to my left. So there's two ethyls. Front carbon? Yeah, two ethyls. Okay, back carbon. I see something going straight down. I see, well, looking at this, I see H on the right. I'm over here, back carbon, H on the right would be bolded. What if I don't draw that in because it's an H? And I see ethyl here. That's not chiral. I'm just going to draw it like that. Actually, that's not chiral over there either. We'll learn about that. We can just leave it like that. It's all good. It's all good. Longest continuous chain, 1, 2, 3. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Is it here, or do we need to come through here? Which 5 is best? The one with the most subs. If we come through here, that's 1, 2. 2 would be a sub, 3 would be a sub, and there. 1, 3, 3 subs if we come through here. If we come through here, how many subs? Only here, there's 2 subs. It's best to come here. This is 1, and either way you go, it doesn't matter over here, 5. So we have a pentane. What's on the pentane? We have a methyl. Let me put it here. There's a methyl there at the 2. What do we have at the 3? A chloro and an ethyl. So this is the main chain, but there's an ethyl, there's a chloro, there's your substituents, methyl, chloro, and ethyl. Alphabetical, right? Which comes first? Chloro. So it would be 3 chloro. What's next? 3 ethyl. 2 methyl pentane. Anybody got that right? There's actually no stereochemistry here. Yes, you have tetrahedral carbons. We'll learn about stereochemistry during test 2. We do not need any stereochemical descriptor. Nothing is needed there. There's no stereochemistry. The only stereochemical descriptor we know at this point is cis and trans, right? That has nothing in there. There's no. Let's see. Did we do this? Did we show this in a perspective drawing? I don't think we've done that yet, have we? Perspective is where you show sort of the ring flat, and you show dashed and wedge. Chairs, you do not show dashed or wedged. It's implied. Stereochemistry is all implied. It's not needed. We draw this flat. I'm not going to worry about possible enantiomers, although maybe I should, but we don't need to talk about it. I'm going to put the isopropyl here and put it like that. So where do you want to put the fluorine? Next door, right? 1, 2. I'll put the fluorine over here. Does it need to be dashed or bold?
Bold. Oh,
It needs to be
dash.
dashed.
Slow down.
Is the isopropyl and the fluorine cis or trans? Cis or trans? They're cis. So we need to draw them cis over here. We're drawing the same compound. Okay, where do you want to put the bromine? Here?
No.
No, the bromine is 1,3 to the fluorine. Fluorine's here, the bromine's here. Is the F and the bromine cis or trans? They're trans, so how do you want to draw it? Yes, it's projected forward. Those two groups are going back if the ring is flat on the board. Bromine's coming forward. Bromine is trans to the other two groups. Everybody agree? It's the same compound there. Is that,
Could you have drawn the isopropyl and the fluorine bolded and then the bromine dashed?
No.
Or are they set in stone like
you
that?
could have, and I would have let you, that would have been okay, but that might have been the mirror image.
Okay.
Which would be called the enantiomer, but we're not ready to talk about that. I did it correctly because on video I don't want to be wrong.
Okay,
Okay,
right,
but you don't know that yet. What you described would work.
okay.
Now, it wouldn't work on the final exam, but it would work on this test. So we don't know enough yet. It's like if I asked you to draw a hand and then I said, you know what, I really want the left hand, you do the right. Or you'd be like, well, why didn't you tell me? So, I'm not telling you because we're not ready to talk about it yet. Down below, I think we did the first one, yeah? How about the one on the right? Boom, 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 boom. Let's put the isopropyl group here. The lowest, I'm thinking isopropyl would be preferred to be equatorial. I'll draw in the H's here. Chlorine would be here. If that is like that, the chlorine is going to be axial equatorial. Or cis. To be cis, the chlorine needs to be equatorial, correct? Are those two substituents cis? Substituents being non-H's. Are these cis? Yes, they're supposed to be cis. Next chlorine comes here. How do we draw it? Axial or equatorial?
So it doesn't matter where you start, right? As long as it's all the same.
As long as the relative position is correct. I actually may have the wrong hand up here, if that's,
I had drawn chlorine axial and one makeup white axial right there. That's where I started. And then went around.
no, I think I got the, I'm good here, just like I was good over there. You did what? Describe what you did, so
I had put my first chlorine axial on that right top piece.
here?
Yeah. And then my hydrogen equatorial. And then the next piece
You can put the chlorine here, but once you put the chlorine here, the next chlorine has to be right next door,
Right,
right?
right.
All that works, all that's good.
Is it the same thing you're talking about where on the final it's not okay, but this one is?
No, it's good. I started with the isopropyl because to me it's the bigger group, and I wanted to make sure it was equatorial. I also just chose to start at this corner. As long as you got the right positioning and it's the right stereochemistry. All groups are cis. Well, they're all cis here. And it's a 1, 3, 4 relationship. Or chlorines are next door to each other, but the isopropyl is, there's a CH2 between them, right? In terms of nomenclature, this would be 1. It'd be 1, 2, 4. It's a 1, 2, 4 relationship. As long as you have that and they're all cis, you're good to go. Is this the best, or do we need to do a ring flip? If we did a ring flip, would that be better? No, it would be worse. These two would go equatorial. No, I'm sorry. These two would go axial, and that would be equatorial. We'd only have one group equatorial. Again, I think the isopropyl is a bigger group. That could be difficult. I will hopefully give you something that's very clear. And you don't have to wonder, well, is an iodine, how does an iodine compare to an isopropyl? That may be actually a little tough. Okay? I will hopefully be clear enough. As your alkyl gets more branched, it becomes bigger and more sterically demanding. As your halogen gets bigger, for us, a bromine would be more demanding than a chlorine. My original is the best, because if I drew a ring flip, I kind of wish it was not the best, then we could do a ring flip. Whenever I do a ring flip, I don't usually, well, all depends on if we're going to worry about stereochemistry or not. I mean, enantiomers, mirror images. Can you show that in a ring flip confirmation? Just do a ring, just show a ring flip. The other confirmation, which we know is going to be the minor confirmation. Question?
Yes. I drew my different, I still did the 1, 2, 4 confirmation, except my orange were both equatorial, and then also the isopropyl.
Chlorines can't both be equatorial. They never can be, no. I see that because here, one's equatorial, one's axial. And the ring flip, do the same thing. That one will become equatorial, and this one will be axial. They can never be the same positioning in terms of equatorial or axial. Why did you, is there any particular reason you drew them both equatorial?
I mean, I was just, when I was doing it, I still did 1, 2, 4, but since they both were on a dash versus wedged, and they're both above a hydrogen. Or,
No, you just,
see, my question is, how do you determine from a cyclohexane, by a wedge or dash to a chair? Like, how do you go from that to, because you can't just go by a wedge and a dash to put on your chair. You go by the hydrogen or being above or below, you call it cis and trans, right?
yeah, these are cis. They're both
Yes.
below the H's.
Yes.
They're supposed to be cis.
So then, how would you draw the dashed hydrogens on that cyclohexane?
You would not. If you drew in the H's here, it would need to be bold.
Exactly.
What do you mean by exactly?
So it's just more like, how would you understand if that chlorine's above that hydrogen, if that chlorine's below the hydrogen.
You just draw it in. That's a straight up bond. Common mistake, you think that these are cis and so they're both equatorial or they're both axial. No. That's not what cis means. Cis does not mean they're both equatorial or both axial. Cis means that they're both below the H. Yes, they are. You see how they're both below? That's why I like to draw in the H's. These two are cis. Now, if this chlorine was here, and it was cis to that one, this would also be axial. So actually, if it was a 1-3 relationship, cis does mean both axial.
It just depends on the-
But I would never have you memorize that. If you're going to memorize it, you've got about 6 or 8 things to memorize. I would not do that. I would just make sure that your halogens are below the H's. That means cis. They're cis, they're cis. Ring flip. Boom, 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 boom. This is actually becomes this point here, and the isopropyl group is now, oh, it is isopropyl. Isopropyl. The other chlorine should be here, and it's going to be axial. And this chlorine is going to be here, and it's equatorial. We're drawing the H's. You see the chlorines are still cis. Everything's still cis. Everything is still below H's, right? I mean, just doing a ring flip doesn't change that orientation. All cis, all cis. Which is better? Well, the original. Because now we have 2 groups axial. Okay, I think this finishes up the material. Do we have any last questions or anything we did not cover? Any last questions? Yes.
You didn't name the IUPAC for the G part of this new production, maybe the structure. Yeah, I don't
What'd you get for the first one here?
I got 2 bromo, 1 fluorine, 2 methylhexane.
I'll do it real quick without stereochemistry here. Boom, boom. We got a carbon, there's carbon. Front carbon has a what? A methyl, a bromine, and a boom, 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 boom. Yeah. Back carbon has a CH2F. Yeah. I can just do that like that. That's the back carbon. It's got 2 H's and an F. Okay. Once we learn stereochemistry, you'll learn when it's important, when it's not. Longest continuous chain, 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. Same thing. If that's the 6, we've only got 2 subs. If this is the 6, which probably is going to be it, if that's the 6, we have 3 subs, an alpha, bromine, and a methyl. 6 is hexane, is that right? One position to be here, you got a sub on the 1, and you got 2 on the 2. Alphabetical would be bromo, 2 bromo, 1 fluoro, methyl hexane. Is that what you said? Okay. This carbon is chiral. And I lost the stereochemistry because I didn't look at it with the correct projections. That's okay. We don't have to do that anyway right yet. If I were to put these on, should I draw the bromine bold or dashed? Twin the planes, one forward. Would the bromine or the methyl be? Well, here's carbon, one in the front, two in the back. With one in the front, two in the back, is the bromine on the right or left? Well, it's right there. One's in the front, two's in the back. In that situation, the bromine is on the right. Okay? This is nomenclature. That's the front carbon. It's on the right. So this would be bolded. It's coming off the page like this. If I'm over here, it's going to the right. The methyl would be dashed. We can put an ME right there if you want to clarify that that's a methyl. Doesn't need it. Because even if it's just drawn like that right there, that's a methyl coming off, right? It's just projected back. So that would be with stereochemistry. It's the same name though. Okay guys, let's take a short 2-minute break. We'll begin with some new material on test 2. It could be that you end up with the mirror image. That's okay. Okay. So let the molecule is chiral. I think it has 2 points, like two hands. Don't worry about it. If you end up drawing the left hand, that's fine. Just have.
Are you going to collect our lab reports?
Yes, I need to collect lab reports. Okay, guys, you've got a green handout. And a white handout. And a blue handout. And maybe that's enough for today. Okay, now I need one from you. Lab reports? Please pass them to the center.
These are the handouts.
Anybody else?
Oh, you got this one.
You got it?
Did you put it?
That's it? You got it?
Hey, mine is supposed
Okay, guys. Put on phone. Okay, test tomorrow. We begin sharply at 9 o'clock. Don't be late. The test will be 55 minutes. Okay, standard length and time for my test. After the test, we'll have lecture after a short break. Unfortunately, that's the way it has to be.
How many questions?
My test typically about 4 or 5 pages. Okay, one page will be IR. Okay. Test 2. Test 2 is largely chemistry of alkenes. And with the carbon-carbon pi bond, much more reactivity, many more types of reactions. We also have alkynes, and we'll have stereochemistry. Largely that there. Test 2 is the only test you'll have with me that does not include any spectroscopy or spectrometry. There's no spectral analysis on test 2. Test 1 we have IR. Test 3 will have mass spec. Organic 2, if you had it with me, every test would have some spectroscopy. Okay, test 2 is not here. Alkenes. Okay, intro to alkenes. All right, the blue there is nomenclature. Okay, that's covered by video only. Should be in the nomenclature folder or something, yeah, on the YouTube page. Please be looking at that sooner than later, of course, after the test tomorrow, okay? Because there's also stereochemical descriptors, which are in the nomenclature, very important. We'll be using that terminology, so you need to be watch that video. Physical properties of alkenes. We'll look at that a little bit. The other handout, the white one is a lot of review about thermodynamics and kinetics. Hopefully it'll look familiar from FinChem. And then the green is moving into reactions. That'll come after the other two. To go along with the green, there'll be another handout. I'll give you that on tomorrow or the next day. Okay, I reckon we can look at physical properties here. I don't think this is on video. I think right here is where we can start. Here's two different alkenes, and we have to get up to this point. First off, are these the same or different compounds? These are different. Why are they different? Because they cannot rotate. They're stuck. First one we would call what? The chlorines are opposite. We can call that trans. Cis trans works with rings. It also works with double bonds, where in both cases the rotation is fixed, either due to the ring or the pi bond. Okay? And so this is trans and this is cis, yeah? Otherwise they have the same exact name. Because they're stereoisomers. Stereoisomers have the same exact name except for some stereochemical descriptor. In this case, that means cis or trans. The name, well, watch the video. Okay, questions about these. Which would have the highest boiling point?
Trans.
Which should have the highest boiling point? Well, which is most polar? Micah? Yes, it has a net molecular dipole moment. It is polar. This one over here is what?
No.
Yes, which one had the highest boiling point? Well, the first answer is the one with the highest IMFs. Which will have the highest IMFs? The one that is polar. And so the positive end of one molecule can attract to the negative end of another molecule. Okay? Highest boiling point. Which is most soluble in water? The polar one or the non-polar one? The polar one. Now, is the polar one actually soluble or miscible with water? These are probably both liquids. Is it? That's an absolute question. Not a relative. Which is most soluble, that's relative. Yes, the polar one should be more soluble in water. Is it? Probably not. But it's got more solubility. Probably doesn't mix completely. Okay? Because this is largely hydrocarbon, and okay. That's a harder question. You may not know. The easier question is relative comparison. As we move forward, we'll do more relative comparison. Absolute question hard. Okay, which one of these two is the most stable? Why trans? What if this was just an alkane and it could rotate? Yeah? Which is better, that or this? This? It's the same thing. This can go both. It's one compound that can do this. Just like I'm one person, I can do this. Am I a different person now? No. But over here it's stuck. But it's the same question. This is more stable with the big chlorines trans. Same here. Here we call it anti and syn. But when you can rotate, cis and trans doesn't work as well. But anti and syn is synonymous with trans and cis. It's the same type of thing. These groups here have more room. Okay? So this is some questions we can ask. Which one's most stable down here? We're looking at alkenes here, yeah? Ah, what is this? These are stereoisomers up here. Are these stereoisomers? No, they're not. And if you name these, nomenclature video, this is called 1, 2, 3, 4. The alkene is at the 1. This is 1-butene. This is what? This is called 2-butene. The 2, the number indicating where the alkene is at. 1, 2, and you just indicate the first. Yes, it's 2, 3, but you just only state the first number. Here, the alkene's at the 1 position. Are those stereoisomers? No, because what do we know about stereoisomers' names? Same exact name. Is that the same exact name? No, then they're not stereoisomers. Now, stereoisomers have the same connectivity. Everything, pi bond. Here the pi bond is connected between 2 and 3. Is the pi bond between 2 and 3 here? No, the pi bond's connected at different positions. Different connectivity. Same formula, different connectivity. That is what? Constitutional isomers. Stereoisomers. Which of these constitutional isomers is most stable? Let's keep going, because this is asked multiple times. Here we have 4 constitutional isomers. They're all. Every one of these has what formula? 1, 2, 3, 4, 5, 6. C6H what? Yes, C6H12. All these have the same formula. Which one's most stable here? Instead of 2, I'll give you 4 to choose from. Okay? Let's look at this table down here. It's the same 4 compounds. Stability of alkene constitutional isomers. The more substituted one is the most stable. Okay? Most stable. Most stable. Least stable. Looking at the alkene. This alkene has how many carbon substituents? The alkene carbons. That alkene carbon has 2. That alkene carbon has 2. 4 carbon substituents on the alkene. How many carbon substituents on this alkene? Only 1, 2, 3, 4. Whenever you're looking at constitutional isomers, the one that has the most carbon substituents on the alkene is going to be the most stable. Why is that? It has to do with the bond strings here. They're all in looking at the carbon-carbon bonds. First off, types of bonds. Every one of these has one sp2 carbon sigma bond. It's the sigma bond that's in the double bond. The difference comes with these other types of bonds. This one has 4 of these and 0 of these. 4 of what? sp2, sp3. See, that's an sp2, sp3. sp2, sp3. sp2, sp3. Okay, you see that? It has 0 of those. But if you go down here, this one only has 1 of those sp2, sp3. The other 3 carbon-carbon sigma bonds are sp3, sp3. Of these 2 down here, which bond type is stronger? That one there. Because it's using an sp2 hybrid, which is a better orbital. Now it's not using it for both orbitals, but one of the orbitals is that. So it has 4 of the strong bonds and none of the weaker ones, whereas you go this way, you have more of the weaker bonds. And that gives you your answer. But we can back it up and say, remember, you look at the alkene, how many carbon substituents does it have? 4. This one only has 1. The explanation is here. So let's go back up here. We already did that one. Of these 4, which is most stable? How about these? Which one's most stable? That one, right? The alkene has 2 carbon substituents. The other alkene only has 1. Now, we first explained this on, I think, Tuesday after Memorial Day at about 10:25. All right? Now, in a week or so, I'll ask you, we'll talk about this, and you guys tend to not remember all this. But I'll remind you that at 10:25 on the day after Memorial Day, we did talk about it. And then we'll talk about it again, and then I'll have to remind you again. Remember the day after Memorial Day when we talked about it? All right. I'm not quite sure why this is always sort of forgotten. And I'm also just sort of getting rid of it a little bit to try to get you to remember this. We will discuss this. This will be the answer to lots of things moving forward. All right? That's how it is with a lot of the material, because organic chemistry builds. Just like we have to understand these bond streams, and we hopefully talked about that for test 1. Okay? What else? Which has the lowest heat of formation? What's a heat of formation? We saw that with cycloalkanes, right? That's the energy that's given off or consumed whenever the compound is made from the elements. In this case, carbon and hydrogen. You take carbon, you react it with hydrogen gas, which is diatomic, and you make that. Okay? You can balance it. You need 6 carbons, right? And I think you need six of those. There you go. That reaction, however it can occur, the thermochemistry there, that's your heat of formation. Right? Hopefully you know that. Which would have the lowest heat of formation? That one, right? Which is also what? It's also the most stable. If this takes a lot of heat, if this takes a lot of energy, does that mean you're making a very stable molecule? If this takes a lot of energy, that means you're making something that has a lot of energy in it. That doesn't sound stable. No. The one with the lowest HF is the most stable. It's the same question. You got to recognize that it's the same question. Which one gives off the most heat when burned? Maybe you're working for a chemical company and you want to use these as fuels. Maybe all these are gases or something. You want to burn these. We burn propane as a fuel, right? We burn butane, methane fuels. What if you want to burn these as fuels? Would you buy the one that gives off the most heat when you burn it, or would you want the one that gives off the least? Well, more bang for your buck. So which one would you buy? If they all cost the same. Which one gives off the most heat when burned? Would that be the most stable or the least? It would actually be the least stable, because least stable equates with highest energy. Which gives off the most heat when burned? The least stable. Which is the least stable? Yes, I'd recommend buying that one. Something that contains a lot of inherent energy, whenever you burn it, it's going to give off all that energy. Yep. There's a question over here you can look at on your own. I think. Yeah. Take a look at that. We'll try to answer it at some point. The effect of double bonds on melting point. Well, we can show an application of this. Do you know fatty acids? You ever heard of trans fatty acids?
Yes.
Are they good for you?
No.
What about saturated fatty acids? Often called just saturated fats. It's good for you? What's the best kind of fats? Fatty. Unsaturated. Well, trans is unsaturated. Did you know that? A trans fat is unsaturated because trans refers to the alkene. That's unsaturated. So you got to be careful what type of unsaturated. The best are your cis. Cis. Okay, here's a saturated fatty acid. The saturation refers to the side chain, all saturated. Now there is a degree of unsaturation here in the carboxylic acid head group. All right? That refers to the side chain. Here's one here. What happened? Did that get cut off? That doesn't look like a long chain fatty acid.
There's a line.
Oh, it's coming down.
Yeah.
Oh, that's because it's a cis double bond, and the cis makes it kink. See, that can be straight. The cis makes it kink. And what does the kink do to the IMFs? Well, what type of IMF do we have out here? Van der Waals. And Van der Waals is just molecules coming here. Okay. Imagine I got 10 arms here. If they're straight, they can all just stack, right? 10 on top of each other. All right? But what if one is kinked? Is it going to be able to stack on top of the other one? Can you imagine stacking 10 bent arms? You're going to have a tough time stacking them. It's the same thing in molecule land. The kink makes them harder to come closer together, and so you don't get as good of IMF, this temporary stickiness from the induced dipoles. Okay, so what does that do to the melting point? That's 69. It's a solid at room temperature. This one's 4 degrees, liquid at room temperature. Which one's more likely to form solid in your veins and arteries or whatnot? The one that's more solid. Now your body's not room temperature, your body's, I think, a little warmer than room temperature, right? More likely to be solid. Saturated fats more likely to form solids. This is going to stay liquid, not form solids as much. That's a simplistic view. Okay? So all these are kink. They all have cis. That's one unsaturation. What do you want to call that type of fatty acid? Monounsaturated. What do you want to call these? Di or poly. Your best are your or your polyunsaturated cis fatty acids. But these tend to be the more natural ones, like in olive oil. Now you can also have fatty acids that have trans double bonds. Now this is a little bit like, it takes more explanation, because this one also has a cis. And yes, it does give a kink, but the presence of trans double bonds actually inherently raises the melting point. I'm not going to try to explain why. Well, I can. This might make sense. Didn't we say that pi electrons are more polarizable? Okay. Well, these are more polarizable, and so it leads to polarization. But it doesn't lead to kinking. So yes, it has some kink, but it also has more polarization that increases IMFs and raises the melting point. So the best is to have only kinking and none of the non-kinking double bonds that raise the polarization. Real quick. Why don't we just use these natural oils all the time? Where did we come up with saturated fats? Where did this come from? They're not natural. These are not that stable. Double bonds can react. They're more reactive. They'll react with oxygen. And your oils will go bad. See, McDonald's doesn't want their oils to go bad. They want to be able to use the oil over and over and over. So chemists have come up with, well, let's saturate them. And once you saturate them, there's no more alkenes, and that will last longer. There's no pi bond to react with oxygen. Yeah, it'll last longer, but it also will clog your arteries. And also, the process of converting cis alkenes to saturated sometimes converts cis to trans. It's a byproduct, a side reaction. So trans is sort of comes whenever they try to saturate it. You end up with some trans. So your natural ones are best. Okay, that's a little bit of fatty acid stuff, but there's chemistry there as well. The explanation. Questions about that? Other things here. By the way, when you do your nomenclature, on the very back, there's 3 alkenes that are named. You might, when you look at it, cover up the name and then try to name it yourself. All right? So maybe some practice here once you do your nomenclature. All right? The other thing you need to look at with the nomenclature, and I pointed this out already, but the idea of stereogenic alkenes. Don't look at the name, but of these 3 alkenes back here, 2 of them are stereogenic, 1 is not. You certainly need to know what stereogenic means. What does genic mean? Just etymology, is that right? Word origin. What is genic? What are some other words? Biogenic? What is genic? Create. Genesis, beginning. It leads to create. So what is stereogenic? Creates stereochemistry. Basically, something about the structure leads to stereochemistry. You got to know when the structure is there's stereochemistry there. If it is, we say the alkene has given rise to stereochemistry. We say it is stereogenic. Okay, that's an intro there. Thermodynamics and kinetics. We can avoid looking at this entire handout if you can answer these 4 questions right here. If you can, we can even end class early. Can you answer all these questions? These questions are about the 2 reactions above. 2 different decomposition reactions. NF3 decomposes into nitrogen and fluorine. And I went ahead and balanced these reactions for you. This is probably the last time you ever see me balance a reaction. All right? For Ni3 going to nitrogen gas and iodine. I give you some bond strengths here. Which reaction of the 2 above gives off the most heat? Gives off the most energy? here's your chance to use your calculator in organic chemistry. You only get 1 or 2 chances. Organic chemistry is not about using calculators, except for lab, where you calculate yields or something. Stoichiometry. Did you do that? Well, if you did number 1, then you can answer which reaction is endothermic. You should also be able to answer which will occur fastest, and are the reactions driven by entropy or not. Those are some questions you should be able to answer. Now, here's a Bond's drink table. We'll be referring to this. I had to give you those because those are not in this table. All right? Hopefully you were able to do those types of questions over there. We'll see a little bit later if you were able to. Please do those. Okay, let's look ahead through this handout. First off, line reactions. What is a line reaction? Well, line reaction is where we show in a line here reactants, like this alkene plus reacting with HBr. And then the arrow here, or these react or yield this product. Now you've seen this before. I don't know if you've ever called this a line reaction. All right. That is a standard reaction of an alkene. Line reactions, you could show sort of the main starting material here, and then your reaction arrow, and put a reagent on the reaction arrow. Where up here I said this plus that. Here okay? So it's variation, very common to put reactants on the arrow. It's also very common to include conditions on the reaction arrow, such as temperature and time. Very common way to show reactions by a line reaction. Okay? Now, got to be careful here. A single line reaction may show multiple steps. There's 2 steps here. First, the alkene is reacting with HBr, such as like that. But then the next step is to react some product formed after 1, which that's actually the product formed after 1. Now we react that with sodium cyanide and we get this product. So the product after number 1 reaction is not shown. And this is where we use 1, 2. You could even have 1, 2, 3. Okay? That would be a multi-step reaction. All right? Now, like with anything, does this make 100% sense? Do you know exactly where you're going to need to use this? No. But as we start doing more and more line reactions, you look back here and say, okay, now I understand what this means. Okay? This is in your notes. As we move along, okay? The relevancy, the context of what we're looking at becomes more clear than right now when you're seeing it for the first time, right? Okay, thermodynamics. All this is review, yeah, you can read, yeah. The take home is Gibbs free energy equation. Delta G equals what? Delta H minus T delta S. You guys familiar with that? Know how to use it? Know what it means? Do you really? All right. Delta H. What is delta H? Enthalpy, heat energy. Directly relates to bond strengths. Positive delta H, the products have gained heat energy. Or you can say the system has gained heat energy, right? Could you also say it like that? Negative delta H, the system has lost energy. Which is more favorable? Negative delta H, right? That'd be more favorable reaction. Delta S is entropy, change in randomness or disorder. Which is favorable, positive or negative delta S? Positive delta S is favored, right? That would be a positive increase in randomness? Yeah. A negative delta S, the system has lost disorder. That's actually a double negative. Losing disorder, that means you have gained order. Gaining order is not good. The system, the universe likes to become random. Just like if I dropped a glass coffee mug right here, it would love to shatter, right? This is our universe. Delta S examples. If this alkene reacts with HBr, we get this product. Delta S is negative. Lost disorder. How is this lost disorder? Two molecules combining to become one. That's becoming more ordered. Thus, it's losing disorder. It's a negative delta S. If we reverse this reaction and show it this way, this molecule breaking apart or decomposing to 2, delta S is positive because one molecule is going to 2. And that's more favorable, right? A positive delta S. How about the third one here? I keep hearing something going ding, ding, ding. Is that a phone? Need to have all cell phones off, including lab. We had people using cell phones in lab last week. Please read the guidelines and requirements for lab. Up here we had 1 to 2, 2 to 1. This is 1 to 1. How do we judge this? The difference here is we made a ring. How is ring going to come into play here? My hands here, I can do all types of things, very random. All right? Yeah? The molecules like to move. We know how they prefer. They prefer maybe anti, but they still move. But what if I make a ring? I cannot move as much. Okay? We have decreased the randomness here by making a ring. Delta S would thus be what? Delta S would be negative, right? Okay? That's assessing delta S. Should be pretty straightforward. Delta H, now note we did not quantify that. We just did a qualitative assessment. Delta H we will quantify. And this is where you'll get to use your calculator. So get your batteries freshened up there. And okay. Here's an example. It's the alkene. It's not quite the same. There's no methyl here. So it's a slightly different alkene we've been showing before. Okay. What do we need to do here? We need to look at bonds broken. We need to look at bonds formed. And we need to do our calculations. Because the delta H equates to bond strengths. We need to see that. Please be looking ahead. We'll pick up here. We'll run through the rest of this handout, which is largely the calculations and also the idea of reaction coordinate diagram. Diagramming the reaction pathways. Then we'll quickly be getting into reactions of alkenes. this. Everybody good? Lab this week on Wednesday, Thursday is the unknown lab. Is that right? Think the unknown lab, yeah? That's tomorrow, right? Today's Tuesday, okay, tomorrow on Thursday. No lab today? Study groups or anything going on this afternoon?
Yeah.
Okay, guys. See you in the morning. Knock it out in the morning. Have a good day, guys.